So our formula for finding the volume of a box was volume equals length times width times height.
Right.
So this is the length, this is the width, that's the height.
Right.
And if you're given the volume, let's say you're given the volume is 140 inches cubed. Let's say the length is 7 inches cubed and the width is 4 inches, or inches cubed, 7 inches, and the width is 4 inches. So what you're looking there, volume equals 7 times 4 times h. You're going to multiply out 7 times 4 is 28. So it's volume equals 28 times h. I should have put it in before, but I put in the 140 for the volume. Should have put it in up here, but the little hamster hasn't quite made it in for the day. So we're going to divide by 28. H equals 5. And the units, of course, would be inches. If this were a technical math course, I would push the units a little bit more. You would start out with this being 140 cubic inches, and this would be 7 inches times 4 inches times h. And when you combine these, 7 inches times 4 inches would be 28 square inches. And then when you divided that out, 28 inches squared, going into 140 inches cubed. 140 divided by 28 is 5. Inches cubed divided by inches squared is just an inch.
I got the answer right, but that's just because I kind of popped the number in there
Sure.
and then multiplied it out.
And you know, that's not a method we teach very often. What you're doing there is called guess and check.
Yeah.
And it is, if you're stumped on a problem, it's a valid problem-solving method. We don't like to teach it because there's other ways that are a little bit more efficient. Like you said, it took a while for you to do it, but you still got the right answer.
Yeah.
You know, if you know that you just multiply these numbers together to get this answer, you can just try numbers until they work. And the big thing with guess and check is it's not just randomly guessing numbers. I mean, the first one you're going to randomly guess and throw in.
Okay, and then go down.
But then you can tell, okay, that number gave me an answer is too big, I got to go smaller. Or that one gave me an answer too small, I got to go bigger.
Okay.
Or it's way too big, so I got to go a lot smaller. So as long as you're doing it intelligently, you know, using those cues to just say, oh, it's wrong, I'm going to try a different number. Well, if it's too big and you go even bigger, you're wasting a little time. You're not being efficient. But
process of elimination.
Yeah. There are more or less efficient ways of doing it. It is a valid problem-solving method. I mean, there are spots in industry. I worked as an engineer for several years. There are spots in industry where that's the only way to solve a problem is to guess. And then once you have that initial guess, you adjust up or down from there. Okay. Any other questions on the homework?
Question number 21.
21. We'll get to that one. Wrong homework assignment. There we go. Why is my Firefox being funny? No, I'm just going to pull it up over here. There we go.
was my internet or if it was Pearson's side, but I was having problems with it this morning.
Kept booting you out.
It kept loading forever, and then it said some unexpected error. Yours did it last night?
Yeah, I think it's Pearson. It had that little circle thing going around for like an hour.
Yeah.
So I just shut my computer down and restarted it, and then gave up.
I took a break.
One thing you can do is play around with different web browsers. I use Firefox because Firefox seems to work better for me.
Okay.
I know my math lab does not work well with Internet Explorer.
Yeah.
You said 21, right? Chrome usually works okay, but sometimes it depends on your... Chrome struggles if your internet connection speed is not high.
Yes.
Chrome itself doesn't like it.
Yeah.
So-
I was doing one last night where it was, around 4 o'clock when I was doing mine, where it was
Yeah.
looking for it.
There are also peak times where you hit, like 7 to 10 o'clock at night is where everybody is doing their homework.
Yeah.
And sometimes Pearson's server gets loaded down.
And my
Does this one look familiar?
Yes.
Okay. So on Monday, Harrison drove X miles on his road trip to visit his parents. On Tuesday, he drove twice the number of miles he drove Monday. If Harrison drove a total of 399 miles on the 2-day trip, how many miles did he drive on Monday?
See, on ours, when I was doing it, it said 555 miles, and not 390.
Okay, so it wasn't divisible by... No, it should have been still divisible by 3. If yours is 555, okay, let's say he did 555 miles, right?
Yeah.
On Monday, he drove X miles. Tuesday, he drove twice as far. That would be 2X miles. So X plus 2X would equal 555. So X plus 2X is 3X. Divide by the 3. X equals 185.
Because I put that in, and it told me it was wrong. Because I tried about 4 different answers in there, and it kept telling me it was wrong.
I'd have to see your... If that happens again like that, hit the Ask My Instructor question, so it'll send me a copy of the exact question you're working on. Otherwise, there's no way I can see the exact question you were working on. Any others on the homework you want me to go through?
I didn't even do them.
Like this one here?
I think I left 8 of them blank.
Okay. That would have been starting about here.
Yeah.
You don't have enough time in class to try to tell me how to do it.
Well, let's take a look. Let's see.
Difficult. It was pretty simple.
There were 3 relationships we looked at. One of them was complementary. That's where they add, 2 angles add to 90 degrees. One was supplementary. That's where they add to 180. And then the other one was vertical angles. That's where they're equal. So those are the 3 situations we dealt with. You know, we said there's really 3 unique situations in any problem different than this. It's 2 things add up to a total, 2 things subtract to make a difference, or 2 things are equal. Well, both of these first ones are 2 things that add up to a total. And this third one is 2 things that have to be equal. None of these deal with a difference. So we have one like this question here, where we have these intersecting lines. This is labeled x and 9x. And what we're asked to find is the value of x. Well, here, because this is a line, these 2 angles have to add up to a straight line, which is 180 degrees. So that means they're supplementary. X plus 9x has to equal 180 degrees. So x plus 9x is 10x. Perfect. We divide by 10 to get x equals 18. And all it was asking for was the value of x. So we are done there.
And then they ask and then you multiply 9x times 18.
Yep, then 9 times 18 is what, 162? This one then is the same thing. It's x and 5x instead of x and 9x. Okay, now this one's a little trickier. This one's not angles, it's rectangles. But we deal with the perimeter of a rectangle. It says the perimeter of the rectangle is 70 centimeters. Then it says that the width, or the length, is 4 times the width. It wants you to find the length and width. When I do a question like this, I'm going to draw a picture, first of all, of my rectangle. Here's my length and here's my width. It says my length is 4 times the width. So the length here is equal to 4 times W. The formula, perimeter equals 2 times the length plus 2 times the width. So that's where I'm starting out with my equation. Do I know P?
Yes.
Yeah, P is 70. I don't know L, but what am I going to do in place of L? L is 4W, so 2 times 4W plus the 2W. The reason I had to do this was because I can't work with two variables. I can't work with both L and W, so I had to get rid of one of them. So I used that relationship between the length and width to replace L with an expression for the width, for 4W in this case. Now I've got to do some solving. I've got to multiply 2 times 4W. Actually, I've got to do some simplifying before I solve. 2 times 4W is 8W. What would be next? 8W and 2W makes 10W. And then? Divide by 10. So W equals 7. So coming up here, the width equals 7. The length equals 4 times W, so 4 times 7 is 28. I always find both of those first. The reason being is the way my math lab asked me to answer the question, I think is backwards. Now this one, it asked for the width first. A lot of times it'll ask for the length first, which is the second thing you really find. So the width was 7. You do have to put in the units. It's a length, so it's just going to be centimeters. Then you got to do the length, which is the 28. That is also centimeters. And there we are. This one's an area formula. You just have a rectangle 15 by 20, so you multiply 15 by 20. These are all area formulas.
I know the one that threw me off a little bit until I kept looking at it was the one for the garden.
Oh, sure. This one here is one I kind of wanted to go over. We didn't do a lot of actually finding areas. We just did like a simple rectangle. But if you have something like this, And that's exactly what you're going to do. 21, 8, 17, 7, 6, and 15. Oops. Got those in the wrong spot. These are all in meters here for now. And as Robin said, you're exactly right. Just cut it like this and you got 3 rectangles. I'm just going to label them 1, 2, and 3. The area of rectangle 1 is just 21 meters by 8 meters, otherwise known as 168 meters squared. Rectangle 2 is a little trickier. It's 7 meters this way. How far is it this way? I can find it right here. That's 21 minus 17 is 4 meters. It has to be 20. If it's 21 here, it has to be 21 on the other side of that rectangle as well. Opposite sides of a rectangle have to be the same length. So that's 7 meters times 4 meters, or 28 meters squared. Then this last one, number 3, is 15 meters by 6 meters, or 90 meters squared. So 280 meters squared if I add them all up. Oh, let's see. Let's go back a few. I think there's some more angle questions in here. Maybe I go forward some. No, mine isn't giving me a lot of angle questions here, but the other situation you could have with these intersecting lines might look like this. You might have 2x plus 28 equals 4x minus 12. What's the relationship between those two angles? Do they add up to a total? Well, do they combine to make a straight line or a right angle?
Yes.
Well, they're on straight lines, but they don't combine to make a straight line, do they? This is a line here. They're going to be equal, exactly. Yeah. These two are the ones that would combine to make a straight line, or these two, right? Yeah, these two are what they call the vertical angles. They have to be equal. They have to be the same. So 2x plus 28 has to equal 4x minus 12. A lot of people get confused here because this is the exact same setup I gave you on a previous problem where I gave you this angle instead of this one. And then they do add up to 180. So anyway, we've got to solve this. What do we have to do? We've got to get rid of one of the variables. There's one on each side, so we're going to subtract the 2x.
2x minus 12.
So 28 equals 2x minus 12. What's our next step?
Divided by 2.
Add the 12. There we go. Got to add the 12 first before we divide. 40 equals 2x. Then divide by 2. So 20 equals x. And now then we have to go back and actually find each of the angles. So 2 times 20 plus 28. 2 times 20 is 40. Plus 28 is 68 degrees. Then I'm going to do the same over here just to make sure I get the same answer. 4 times 20 minus 12. 4 times 20 is 80. Minus 12 is 68 degrees. So 68 degrees seems to be the consensus there. I know I didn't cover a lot of angle problems for you, but hopefully that helps out a little bit. We will come back and we will see more of those again at another point in the course. Any other questions off the homework that you want to see? Okay, so new stuff. We're going to start off today talking about factors. What is a factor? Well, a factor is a number that divides into another number. It divides into a desired number. That's one of the definitions. The technical definition of a factor is a factor that is a piece that can be used to build something bigger. Outside of math, that is the general definition of a factor. Is used to build something larger. If you're creating a product, you have factors, you have ingredients that go into it. Well, and funny I should use the word product because that's how a factor is used to build a larger number. Let's say I have the number 12 and I want to know factors of 12. I could do 2 times 6. That would be a factor pair of 12 because they multiply up to make 12. I could do 3 times 4 would multiply to make 12. Now there's another one. 1 times 12 makes 12. We don't count that as factors because that's just 1 in the number itself. And every number can be created by multiplying 1 times itself. So you're not really building it from something smaller. Notice it's used to build something larger. So 1 times 12, you're not using, 12 isn't building something larger, it's building itself, so that doesn't count as a factor. So all of the factors of 12 we listed these out. There's 2, 3, 4, and 6. All of those are factors of 12. All of those can be used in some combination to build a 12 or to multiply up to a 12. Also, twelve is what we call divisible by each of those numbers. Divisible. To be divisible by a number. Means to divide without a remainder. I mean, I can divide 12 by 5, but I get a remainder or I get a decimal or a fraction. So if I want to come up with factors of 36, I don't know why I wrote it that way. Let's do factors of 36. Obviously, well, 1 isn't going to work, right? 9 times 4 is a factor pair. You are correct. Let's just kind of count up. 1 we said doesn't count. 2 goes into it. What's after 2? What's the next one? Does 3 go into it?
4.
3 does go into it, yep. Does 4?
Yes.
Yep. 5?
No.
No. 6? 7?
No.
No. 8?
Yep.
Careful.
No, it doesn't.
8 does not. 8 gets 32 and 40.
Yeah.
9?
Yes.
Yes. 10?
No.
No.
No. 11? No. 12?
Yes.
Yes, it does. 13. Nope. 14? 15?
No.
16?
No.
17?
No.
18?
Yes.
Yes. Now I'm going to stop at 18 for two reasons. One, because I know it's the last factor. Two, I know there can't be any factors bigger than 18. Why do I know that? Well, we said you can't divide the number by 1, right? So what's the smallest number you can divide a number by?
2.
2. If I divide 36 by 2, I get 18. So there can't be anything bigger than 18 because there's no other number that could multiply it to make 36. So when you get up to the half of the number, you get up halfway, you can stop there because there's nothing between half of the number and the number itself. Now what we did there is we actually did count up and did one by one to see if it worked. If you don't know, you can take your calculator and try to divide them out and make sure there's no decimal afterwards. But that's kind of tedious. So there are divisibility rules. That help us determine if a number can be divided by certain smaller numbers. Bless you. How do we know if a number can be divided by 2? The number is even. Now, generally, we got to discuss a little bit, what does it mean to be even? Well, a lot of people define even as divisible by 2, right? Even means the last digit is 2, 4, 6, 8, or 0. So basically, if the last digit of a number is divisible by 2, the whole number is divisible by 2. So here, is that number divisible by 2? Yes, it is, because that digit's divisible by 2. Does anybody know the divisibility rule for 3? It's the sum of the digits. Let's use that 478,266 to demonstrate what I mean. We're going to add up the digits. What is 4 plus 7? 11. Plus 8? 19. Plus 2? 21. Plus 6? 27. Plus another 6? 33. Is 33 divisible by 3? Yes, it is. If you didn't know, by the way, you could keep going. 3 plus 3 is 6. 6 is divisible by 3, right? So 33 is divisible by 3. 478,266 is divisible by 3. Because when you add up the digits, the sum of the digits is divisible by 3. Four has a divisibility rule, but it's a little tricky to use. I'm going to show it to you in just a second. But most of the time when we're trying to divide numbers and trying to factor, we're not really looking for factor pairs. We're looking for something we're going to call prime factors. So you want the smallest numbers. So a 4, if you divided by 2 twice, that'd be the same as dividing by 4, right? So really, you don't need a specific rule for 4. But there is one. The rule for 4, similar to the rule for 2. 2 is if the last digit's divisible by 2, or in other words, it's even. Well, for 4, it's the last 2 digits. So if I have a number like 293,768, all I care about are the last two digits, the 68. Is 68 divisible by 4? It is. Now, that rule is only useful and handy. I mean, these rules, divisibility rules, are meant to save you time and make it quicker. Well, the only way this rule makes your life quicker is if you've memorized all the multiples of 4 up to 100. Most of you, I'm guessing, haven't done that. I will say that all you have to do is divide by 2 twice. So take 68. What's 68 divided by 2?
It's 34.
34. What's 34 divided by 2? 17, right? So it divides by 4 if it divides by 2 twice. So that rule for 4 is a little bit not as convenient, not as useful as the 2 and the 3. How about for 5? Most people know how to tell if something's divisible by 5. Yes, the last digit is 5 or 0. And this is usually the first one I look for. In fact, generally I look for zeros first. If it ends in a 0, that means it's divisible by 5 or 10, right? So I usually look for 0 first, then I look for a 5. If there's no 0, then was it divisible by 5? Then I'll go down to the 2 and the 3 and so on. So if I have the number 3,925,785, that is divisible by 5 because that last digit's a 5. Six, again, is not as convenient. It's divisible by 6 if it's divisible by both 2 and 3. Is this one divisible by 6? Well, before you start adding up the digits, always check, is this divisible by 2?
No.
No. So it's not. So check the 2 first. It's a lot simpler. You just have to look at that last digit, see if it's even. A lot of people start adding up the digit and say, oh, it is divisible by 3. Well, it wasn't divisible by 2, so you did a lot of work for nothing. This one, is it divisible by 2?
Yeah.
Yes, it is. Is it divisible by 3? Well, 7 plus 5 is 12 plus 1, 13 plus 5, 18 plus 8, 26 plus 4, 30. Is 30 divisible by 3? Yes, so this is divisible by 6 because it's divisible by both 2 and 3. Anybody know the divisibility rule for 7? Well, unfortunately, I don't either. As far as I know, there isn't one. But if one of you guys can figure one out before the end of the summer and let me know, I will give you an A in a class because I'm going to publish it and get rich and retire.
Or we didn't have to practice it.
You get an A in the class. What more do you want? Don't get greedy on me. I'm just kidding. So there is no rule for 7. Actually, throughout history, most of the people that are famous for coming up with math, things like Pythagorean theorem, stuff like that, Pythagorean theorem was not found by Pythagoras. It was found by one of the students in his school. He actually had a school that he ran. It was found by one of his students. But guess who gets credit for it? The student didn't have the firepower to publish it and get it out there. Pythagoras did. So
Edison and Tesla.
yeah. Well, Edison and Tesla were kind of different. They were competitors, not really.
And Tesla worked for it.
Worked for Edison at first. Realized that he knew more than Edison did.
Edison was good at stealing people's ideas.
Number 8, or for 8. Similar to the rules for 2 and 4. 2 is divisible by 2 if the last digit is divisible by 2. You're divisible by 4 if the last 2 digits are divisible by 4. You're divisible by 8 if the last 3 digits are divisible by 8. I'll get back here. So if I have something like this, 796,624. That would be divisible by 8 if 624 is divisible by 8. Anybody know off the top of their head if that's divisible by 8? Yeah, it is. 624 is divisible by 8. Now again, that rule is only handy if you have all the multiples of 8 memorized up to 1,000. And again, I'm guessing not all of you do. I'll be honest, I'd be shocked if any of you had all of them memorized. I don't, so don't feel bad. 9. It's the same rule as 3. It's the sum of the digits again. I think that'll work. Let's see. So if I add them up, what is 7 plus 9? 16 plus 6? 22 plus another 6? 28 plus 3? 31 plus 5? 36. Is 36 divisible by 9? Yes. So that whole number is divisible by 9. How about 10? Yeah, the last digit is 0. So it's really easy to tell something's divisible by 10. We could have 59,283,764,390. All that we care about is the 0. That is divisible by 10. There are divisibility rules as we move up the ladder, and I'm going to show you one of them at least in a little bit. The problem with those divisibility rules as we go up to larger numbers is they get more and more complicated. Like even for the 8, that one's not real handy because you have to know if that 3-digit number is divisible by 8. Well, we don't work with a lot of numbers by hand that are bigger than 3 digits, so it's not real helpful. 9, we really didn't need a rule for 9 because to divide by 9, we could just divide by 3 twice. We said the same thing for 6. Rather than telling if it's divisible by 6, we just divide by 2 and by 3, and we've divided out of 6. For 8, we don't really need that rule because we can divide by 2 3 times. 2 times 2 times 2 makes 8. So if we divide out of 2 3 times, we've divided out an 8. So before we move on to the next divisibility rule, I want to talk about something called prime and composite as it applies to numbers. The word composite means something made up of smaller components. I'm sure most of you have heard the phrase composite materials. Composite decking for putting decks on your house or whatever. Composite means it's made up of more than one type of material. Like most composite decking is wood and plastic or wood and some other material embedded into it. A composite number has factors. In other words, it can be made up by multiplying smaller numbers together. Prime has no factors. In other words, the only numbers that will divide a prime number are 1 and itself. And those aren't factors, remember. So the reason we didn't really need divisibility rules for like 4, 6, 8, and 9, although we had divisibility rules for all of them, we didn't really need divisibility rules because they are composite numbers. They're made up of smaller numbers. 4 is equal to 2 times 2, so we just divide by 2 twice. 6 was equal to 2 times 3, so if you divide by 2 and divide by 3, you can divide by 6. 8, 2 times 2 times 2. Like I said, divide by 2 3 times. 9 is 3 times 3. Divide by 3 twice, you've done the 9. 12. 2 times 2 times 3, right? So if you can divide by 2 twice and 3, you can divide by 12. And technically the divisibility rule for 12 is if you can divide by 4 and 3, you can divide by 12. So you don't need divisibility rules for these larger numbers because we can cover it by looking at the divisibility rules for its factors. So any composite number you don't need a divisibility rule for. Now like 14 is 2 times 7. However, we don't have a divisibility rule for 7, so there is no divisibility rule for 14 either. So as we move up the ladder, the only numbers that they have divisibility rules for are prime numbers. Numbers that cannot be broke down into small numbers are made by multiplying smaller numbers. Well, as we get bigger from 10, 11 is the next number up, and it is a prime number. Now, I warned you that as we get larger than 10, the divisibility rules get really difficult. You do not have to write this one down. You'll never be quizzed on it or tested on it, but it might be handy to know. The divisibility rule for 10 involves a few-step process. Let's start out by taking a number like 283,700 and, well, let's see what I need here. Let's go 12. First of all, I'm going to take my calculator and I'm going to test it. No decimal, right? So that does divide by 11. Well, let's look and see what our divisibility rule tells us. The divisibility rule says you start with the first digit and you take every other digit after that. And you add them up. What is 2 plus 3? 5 plus 1 is 6. So I get 6 there. Then you take the remaining digits. 8 plus 7 is 15 plus 2 is 17. And you look at the difference between those. What is 17 minus 6? 11. If that difference is 0 or divisible by 11, then the whole number is divisible by 11. So that obviously 11 is divisible by itself. So 283,712 is divisible by 11, as we saw. Now, realistically, I remember that process because I'm a math geek and I like weird stuff like that. I don't expect any of you to remember that little process in about 7 minutes. Just because it's not something you're going to use that often. And as we go up the ladder, there is divisibility rules for like 13 and 17. but they're not horribly useful because they're complicated. And with calculators, you just punch them in the calculator, you're going to get the answer, you're going to get a result, and you can tell whether it's divisible if there's no decimal or not. So it's not really that handy as we move up the ladder. So we can tell if these numbers are divisible by another number. Now we had mentioned that for a number like 36, there are several factor pairs. There's 2 times 18, 3 times 12, 4 times 9, and 6 times 6. All of those are factor pairs that could be used to create 36. If I ask you to factor 36, how do you know which pair I'm asking for? Well, the answer is you don't. So how do you know which one to put down? Well, generally we don't ask for factor pairs. I mean, we might in your homework just to practice it a little bit. But generally what we're asking for is prime factor. So if I ask you to prime factor 36, what I'm asking you to do is to break it down, and it's probably going to take more than just a pair of numbers to do it. Break it down in the smallest numbers that can be used to build up to 36, down to prime numbers, so that none of them can be divided anymore. And we do that by using a factor tree. What is any number that divides into 36? 2. Perfect. 36 is divisible by 2. If I divide 36 by 2, what's left? 18. Now look at these. 2 is prime, so I'm going to circle it. I can't split 2 up anymore. 18, can I split that up? What's one number that goes into 18? 9 does. What's left over? 18 divided by 9 would be 2. Perfect. So that 2 is prime. Can 9 be split up? Okay, what's a number that goes into 9? 3. If I did 9 divided by 3, what's left over? 3. Both of those are prime, so I'm going to circle both of them. And we're done. Everything is prime. So the prime factoring of 36, and I'll write them from smallest to largest, 2 times 2 times 3 times 3. That's the prime factor. Now, this is written out in long form. Sometimes it's easier to write it out in exponential form. What does that mean? Well, 2 times 2 is just 2 squared. 3 times 3 would be 3 squared. So yes, 2 squared times 3 squared. If I ask you to prime factor 40. Now, I told you there's kind of a process I go through. The first thing I look for is 10s and then 5s. Well, is this divisible by 10 or 5? Yes, in fact, it's divisible by 10, right? So if I divide by 10, what's left over? 4. Good. Are either of those prime? No. So I'm going to go down to each of them can be split up. 10. Obviously, I'm not going to divide by 10. Is it divisible by 5? Yes. If I divide it by 5, what's left? 2. Both of those are prime, so I'm going to circle them. Going over here, 4 is not divisible by 10 or 5. The next thing I usually look at is 2's. Can 4 be divided by 2? Yep. What's left over? 2. The next thing I would look for is see if it's divisible by 3. We just didn't get that far. We got hit prime factors before we had to worry about 3's. And then after a 3, that's when I'd usually look at 7. Because 5, 2, and 3 cover all the numbers from 1 to 10 except for a 7. So, and the 7 has no rule. So that's kind of the list I go through as I'm looking for factors. Anyway, we've got it prime factored here. 40 is equal to 2 times 2 times 2 times 5. Or if I did that in exponential form, perfect. 40 equals 2 to the third times 5. Any questions? Okay, now as we go through here, these factors in factoring actually have a huge role in a lot of the processes we do in math. We look for like greatest common factors or least common multiples. And there are things we get used to doing just by trying to look for them in our mind, guessing the numbers or trying numbers or whatever. But they can actually be found by doing factoring and doing a process with the factors to find those values. And as we encounter them, we will look at those. So we used exponents here a little bit. So I want to take a little bit of time here before we hit our break to talk about reviewing our exponents. Rules of exponents. Of course, we know that x to the third means what? Perfect. X times x times x. And we said that if I had x to the third times x to the fifth, what did I get? X to the eighth. We are multiplying, but the appearance is that the powers just get added together. Because x to the third is 3 x's multiplied together. X to the fifth is 5 x's multiplied together. If we multiply them all together, we now have 8 x's being multiplied together. So what if I have y to the 7th times y to the 18th? What do I get? Yes, y to the 25th. When I'm multiplying exponents with like bases, I can add the powers. So 7 plus 18 is 25. How about z to the 4th times p to the 8th? Yeah, I can't combine them. Why did I change the order of them? Just to confuse you. Notice I took out the multiplication too. What was that? Alphabetical order. We talked a little bit about grammar having the highest power first when we had different digits. Another grammar thing is when we have more than one variable on the same term or same digit. And this is one digit. Technically, this is 1 p to the 8th z to the 4th. One count with its names. Technically, it is better mathematical grammar to put them in alphabetical order. That's why x usually comes before y, and y usually comes before z. P comes before z because it's alphabetically. Now I want to point this out here. When I'm multiplying algebraic numbers, remember, anytime we multiply, we first combine the counts. What are the counts here? 7 and 12. We combine those, what do we get? 84. We are multiplying, so we're still combining with multiplication. And then we combine the names. The x to the 5th and the x to the 9th make x to the 14th. Now, I'm glad that you said 19 there because I was hoping somebody would. because it gets confusing because when we're looking at these, we're multiplying. But when we multiply, we add powers. So it's easy to say, oh, we're just going to add 7 and 8 and 7 and 12 too to make 19. No, we are still multiplying. So when we combine counts, we do have to multiply 7 times 12 to get 84. We are multiplying x to the 5th times x to the 9th as well. Like we said, it's just the appearance is that the powers get added. So if we had 3, I'll change variable here, y to the 21st times 5, y to the 13th, what do we get? 15y to the 34. Very good. You multiply the counts. 3 times 5 is 15. You multiply the names. Y to the 21st times y to the 13th. The appearance is you add the powers. 21 plus 13 is 34. What if we have more than one variable? We have 7 x to the 5th, y to the 8th, times 3 x to the 6th, y to the 4th. Now, we still combine the counts. 7 times 3 is 21. Now we can combine each name separately. X to the 5th times x to the 6th. X to the 11th. Good. Y to the 8th times y to the 4th. Y to the 12th. Perfect. Now, I'm going to do a couple wrong. And I want you guys to look at them and tell me what I've done wrong. Can anybody tell me what I did wrong there?
You multiply the powers.
I multiplied the powers. Yeah. What should I get for an answer?
X to the 10th. Y to the 7th.
Perfect. 8 times 5 is 40. X to the 8th times x squared, you just do 8 plus 2 is 10, x to the 10th. And y to the 3rd times y to the 4th, 3 plus 4 is 7. So y to the 7th. Wonderful. How about this next one? So I have 12, a to the 9th, b to the 11th, times 9, a to the 3rd, b to the 5th. Get 21, a to the 12th, b to the 16th. Okay. I didn't multiply the 12 and the 9. I added them. So what the answer should be here, I'll give you the 12 times 9 is 108. Perfect. A to the 12th and b to the 16th. Any questions? We've looked at multiplying larger things. Like this. Now we looked at it, really the long way of doing it, I shouldn't say long way, the full way of doing it was to write it out. 7x squared minus 3 times 5x to the 3rd. Then we multiplied out each piece. 5x to the 3rd times negative 3x, negative 15x to the 4th. 5x to the 3rd times 7x squared, 35x to the 5th. That is the full way of doing it, the actual way of doing it. But because this happens so much, we learned that shortcut called distributing, where I just take the 5x to the third times the 7x squared is x to the fifth, 35x to the fifth, good. And 5x to the third times negative 3x, negative 15x to the fourth. We get the same answer, it's just this way is a little quicker. It's also saves space, so we can do it right in the problem when we're solving equations and stuff like that. And we saw some kind of ugly problems. Like on our test, we had one similar to this. Tell me what to do here.
You have to distribute the negative 5y to the third inside boxes.
Perfect. We see that parentheses, and there's nothing we can do inside there. But there's something that needs to be done to them, and that is multiplying by the 5y to the third. So I'm going to leave the 3y to the seventh up front, doesn't change. Negative 5y to the third times 4y to the sixth is negative 20y to the ninth. Very good. Negative 5y to the third times negative 2y to the fourth.
Positive 10.
Positive 10. Y to the seventh. Good. Now we've got the negative 7y to the ninth tacked on the end. What do we combine? Well, we got to combine like powers. Yeah, they're all y's, but we have to have the same power. And remember, grammar says we do the larger power first. So the y to the ninth. Negative 20 and negative 7 make
Negative 27.
negative 27. There we go. Y to the ninth still. 3x to the seventh and 3x to the seventh and 10x to the seventh is 13. It should be y to the seventh. I said x, but yes. Y to the seventh. One that we haven't encountered yet is one that looks like this. So this should have been y to the fourth up front here. Let me change that. So 5x to the fourth minus, in parentheses, 3x to the fourth minus 2x squared plus 4x squared. So we see the parentheses. Is there anything to do inside the parentheses? Say no. No. Is there anything being done to the parentheses? Well, there's a minus there, but the minus is acting on the parentheses, not on any other number, right? What that really is, we've talked about ones that are there, we just don't write them. Like, x to the fifth is really 1x to the fifth, we just don't write it. Or 2x is really 2x to the power of 1, we just don't write that 1 in there. Here's another spot where there is a 1 that we just didn't write in. That is really negative 1 times that parentheses. So to solve that, we have to multiply through by negative 1. So the 5x to the fourth doesn't change. Negative 1 times 3x to the fourth? Negative 3x to the fourth, good. Negative 1 times negative 2x squared? Positive 2x squared. And then we still have the positive 4x squared on the end. So now we can combine. Yep, 5x to the fourth and negative 3x to the fourth. 2x to the fourth. 2x squared and 4x squared. 6x squared. Very good. So that's another one of those spots where you got to be careful. There's a 1 there. We just don't write it. And it's much simpler if you put that 1 in there. And the way the textbook describes it is you have that minus in front of the parentheses, or you just change all the signs in the parentheses, which is basically what we did. Positive 3x to the 4th became negative 3x to the 4th. Negative 2x squared became positive 2x squared. But the reason you can just change those signs is because you're multiplying by negative 1. So some of our other operations with these numbers that we've looked at. Addition. Now that we know powers, we can look at our place values again. This is the ones place, the tens place, the hundreds place, the 1,000s, the 10,000s, and so on. 100,000s, 1 millions, and we can stop there. Now that we know a little bit about powers, we know that 10 is really 10 to the power of 1. We know 100 is 10 to the power of 2, right?
Oh, yeah.
Our number system is called a decimal number system. The term decimal means base 10. Our place values are exponents. Remember we said an exponent has 2 parts, a base and a power? They're exponents with a base of 10. So it's a base 10 number system. So this is 10 to the 3rd, 10 to the 4th, 10 to the 5th. This is 10 to the 0. Remember, anything to the power of 0 is 1. I could have y to the power of 0. It doesn't matter what value y is. Y to the 0 is 1. That's the one power of a variable that we can evaluate every time. It doesn't matter what the value of the variable is. If it's the power of 0, it must be 1. That also explains our decimal place values as we go this way, by the way. We get into negative powers, which we're not quite ready to talk about yet. We'll deal with those in a little bit. What we're looking at is in algebraic numbers. Is a similar place value system. Only the exponents don't have a base of 10. Let me show you what I mean. If I had a number 347, then we could write that out as 3 hundreds and 4 tens and 7 ones. Well, a shortcut would be 3 times 10 squared, that's hundreds, right? And 2 times 10 to the 1, or just 10, that's the tens, plus, I don't know why I put 2 there, that should be a 4, right? 4 times 10 to the 1, or just 10, plus 7, and we don't have to write out the 10 to the 0, we just leave it as a 7. Notice what I put here are my place values. The ones don't really get written in. If I compare that to an algebraic number, you see it's the same. Instead of 3 times 10 to the second, it's 5 times, well, instead of 10 to the second power, it's x to the second power. 7, instead of 7 times 10, it's just 7 times x. 3 ones, well, that's x to the 0. Right? You can see here an algebraic number is the same as our whole numbers. It's just our place values have a base of x instead of a base of 10. So they behave exactly the same way. When we added algebraic numbers. This look familiar yet? We did it exactly the same as we did whole numbers. We write the first number out, and we line up the place values. 7x squared goes under the 3x squared. 2x goes under the 7x. 9 ones goes under the 5 ones. And we added our columns. 5 and 9 is 14. 7x and 2x is 9x. 3x squared and 7x squared is 10x squared. The exact same process. It's just the place values are x's instead of 10s. Now, one of the things we saw was in algebraic numbers, each digit can be positive or negative on its own, which causes a little confusion, but we can get through that. Okay, it is our break time, so let's go ahead and take our break. We'll come back and look a little bit more at working with algebraic numbers and then some other things. So let's come back about 10:25.